Okay, so a couple more divisibility results to look at. So the first one, it's very similar to the last theorem. In fact, we could almost call it, we could call it, rather than a theorem, a corollary. And a corollary is just a fancy word for a result that comes from a previous theorem almost immediately. And this result comes from Theorem 39.5, which was the last theorem in the last video, which said if n was a number and n divided ab, and what else do we need? That n was relatively prime with a, then n must divide b. So this is very close to that. So there's kind of two results here. So case 1 is kind of obvious. What if p divides a? Then we're done. We're going to do two cases, p divides a or p doesn't divide a. So if p divides a, it's immediate. So that's pretty easy. And case 2, which is the other case, so case 2, maybe I'll plus, since I used Roman numerals for that case, let's use it for case 2 as well. So that's p doesn't divide a. P isn't a factor of a. So since p is prime, well, the GCD of p and a has to be 1. If p isn't the divisor of a, well, p has exactly two divisors, one in itself, so the greatest common divisor, if it's not p, has to be 1. Well, now we can just apply Theorem 39.5. So applying Theorem 39.5, we're in the situation where p divides ab, and the GCD of p and a is 1. So we're in the perfect situation for 39.5. We get that p must be a factor of b. So there are two exhaustive cases, so we have the result we want. When p divides a, which is immediate, and then when p doesn't divide a. That exhausts all possibilities, and in each possibility, our theorem is true, so we've proved what we wanted. Now here's a result that we can prove, in fact, by induction. There's nothing stopping us from having this result with more than two numbers. So let's let a1 all the way to, say, an be integers. What else do we need? Where the number of integers is greater than or equal to 2. Then, if p is a factor of the product of these guys, a1 times a2 all the way to times an, then of course p is a factor of one of these numbers for some I in the set of the numbers from 1 all the way up to n. So p divides at least one of our AIs. And the proof of this is going to be by induction. And we're going to induct on the number of numbers we are multiplying together. So our base case is, of course, when n equals 2. And basically, this is just Theorem 39.6. That's literally what we just showed. Now, let me scroll down a little bit. Our inductive case is going to be the following. So we're going to assume that the result holds for some k greater than or equal to 2. So that P is a factor of one of the AI's from 1 up to k. So that's saying if P is a factor of our A1 all the way up to AK, then P is a factor of some AI. I'll just write this for some I in the set from 1 to k. So that's what we're assuming. And we need to show if P is a factor of the numbers from A1 up to AK plus 1, then P is a factor of one of the AI's, where I goes from 1 all the way up to K plus 1. Make that a little neater. There we are. So, if we think about this, we can consider A1 times A2 all the way up to times AK times AK plus 1. So we can group it as follows. Remember, we're always using a chance to use our induction. So we're going to consider that where, now I'm going to write this a little loose, P divides this, because I just screwed up the notation a little bit, but that's okay. All right, so what this means is basically the same thing as the other case, as the other corollary. We can break this into two cases. So case 1 is if P is a factor of A1 all the way up. Maybe I'll do my dots a little differently. A1 all the way up to AK multiplied together. If that's the case, by our inductive hypothesis, we have that P is a factor of AI for some I in the set from 1 all the way up to K. So we're done just by our inductive hypothesis. But we have another case which is basically going to be the same thing as in the previous corollary. So case 2 is if P isn't a factor of that product of A1 up to AK. So this means that the greatest common divisor of P and A1, all the way up to AK multiplied together, so those two numbers. We're thinking of this guy, remember, as one number. Well, there are two divisors of P, one and itself, and if itself isn't the divisor, then it must be 1. So we can apply Theorem 39.5. So that means that P must be a factor of AK plus 1. So you can see by induction, we have our result. And the place where we used our inductive hypothesis was in case 1. So we looked at this product, and we're assuming that P divides this product. So using our inductive hypothesis is breaking our product into basically two numbers using the associative property. The number A1 all the way to AK multiplied together, and then AK plus 1 by itself. Remember, when you're doing an induction, you're always looking for a chance to use your inductive hypothesis, and here it is here. So, just like the previous result, if I used the inductive hypothesis in case 1, so P is a factor of A1 all the way to AK multiplied together, that's our inductive hypothesis, so P is a factor of some AI. In case 2, P isn't a factor of our product there, so that means that the greatest common divisor of P and that product is 1. So that means by Theorem 39.5, which you've already proved, so we might as well use it, P must be a factor of the other number, AK plus 1. And we're done. We can say by induction, let's write that actually. So by induction, our result is proved. And you can kind of see how mathematics works in this case, where we're building slowly. We just have one theorem and then a bunch of corollaries that follow from it. That's a fine way of doing mathematics. I mean, if you want to go back and clean things up, you might be able to be a little bit careful and put this all into one result. But for our case, for our purposes, this is fine. This really shows kind of a nice mathematical process. Alright, let's try the following result here. So we're going to take three integers, a, b, and c, and a and b are going to be relatively prime. So that means that the greatest common divisor is 1. They have no common factors besides 1, of course. Well, if both a and b are factors of c, well, that means that their product, AB, is also a factor of C. So let's take a look at that. So here's the proof of what I wanted to show. So we know that A and B are co-prime. They're relatively prime. So that means their GCD is 1. We know by Theorem 39.3 that AXC plus BYC equals C for some x and y that are integers. We can write C as a linear combination of A and B. That's the nice thing about numbers being relatively prime. We can write any number as a linear combination of relatively prime integers. So, we also know, since A is a factor of C and B is a factor of C, well, we can write C as A times, let's say, K, and C also as B times L for some integers, K and L. So we know those things are true. So remember, we want to show that AB is a factor of C. It would be nice if we could pull out a factor of AB in each of these two terms on the left-hand side. Well, I already have an A here. If I could get a B somewhere else here, and if I have a b here, I could get an a somewhere else here. I could do that. But remember, I have the c factor, so I can substitute b ln for this c. That would give me an a and a b, so I could factor an ab from the first term, and the other way around. Here is another c. I can write c as a times k, so if I replace this c with ak, I can factor out the a and the b here, and we're done. So let's do that. So let's call this 1 and 2, and let's call this star. So subbing in 1 and 2 into star, well, what do we get? We get that ax times bl, so that's using 2 here, plus by times ak, that's using 1 here, that equals c. So we can factor out the ab from both terms. So we have ab times xl plus ab times yk equals c. So since, well, xl plus yk, that's an integer. Since we're just adding and multiplying other integers, we know we have an integer. So since that sum and product is an integer, we know that ab is a factor of c, and we're done. Now, using those results, we can cover what is probably the most important theorem in this section. It says that every number has a unique representation as a product of prime numbers, up to order. You can, of course, commutativity holds, so you can move things around if you want, but the primes are the building blocks of all other numbers uniquely. So that's what we're going to show next. So the next result, as I said, is this fundamental theorem of arithmetic. This is kind of the piece de resistance. So it says, any integer greater than or equal to 2 is either prime or it's a product of a bunch of prime numbers. And that product is unique, up to order. So we're going to prove this in 2 parts. So you can see here, there's 2 things it's telling. It's telling you it's either prime or there exists a factorization into a product of primes, which we'll call a prime factorization. So we need to prove that the prime factorization exists. So we need an existence bit. And then once we get an existence bit, we need to show that it can only be done in one way. So we need a uniqueness bit. So we have 2 bits to do in this proof. So let's do the first bit. Let's do existence. And the way we're going to show this is via induction. In fact, we're going to use strong induction. This is an excellent example of strong induction where we're not using a base case or base cases where we're just using those number of terms. This is an actual use of strong induction and not k-step induction in some sense. So I think it called induction by step T or something. Whatever I called it, this is proper strong induction at its most useful. So let's do it by strong induction. So our base case, well, that's when n is 2, 2 is prime. So since 2 is prime, it's either prime or a product of primes. So we're good to go. Our base case is indeed satisfied. So for our inductive case, we're going to assume that n is prime or a product of primes for all n such that, well, n is between the smallest value in our base case 2 and some k. So we're going to assume it's true for some value k and every number below that as well. And we want to show that k plus 1 is prime or a product of primes. Okay, so that's what we want to show. Maybe put some brackets around that. That's our goal. Okay, so let's consider k plus 1. Well, there's two cases here. So the first case, well, maybe k plus 1 is prime. If k plus 1 is prime, well, then we're done. The theorem is satisfied. So the theorem is satisfied. We've proved our result. No problem. But case 2 is that k plus 1 is not prime, so it's composite. Well, if k plus 1 is composite, this means that it has two factors. That we can write k plus 1 as a times b for some a and b in the natural numbers, and also, I should say, not even the natural numbers. It's in fact, we don't need it to be 1. We can pick two ones that are 2 or greater, so let's use that same domain. And of course, a and b are both less than or equal to k. So this is where we can use our induction hypothesis. Thus, a and b can be expressed as a product of primes. So we can write k plus 1 as, let's say, p1 times p2 all the way to, say, pk. So they're going to be the product of primes that make up a, because a is smaller than k, so our inductive hypothesis holds. And then our other primes are going to be q. So q1 times q2 all the way up to ql. I shouldn't use k here, sorry. This is a bad variable choice because I've already used k. I'm just so used to using k as an index. Let me use something else. How about l? Let's use m. So there's m primes that multiply together to give you a. So we're thinking of this as a, and this is b. And this is true, let's say, by our inductive hypothesis. Awesome. Thus, well, we're done. Oh, let me write that in black. Thus, k plus 1 is a product of primes. So, we know that every number can be expressed as a product of primes, so by induction, the existence is proved. So we know that at least one exists. We just have to show that exactly one exists. So the next part of our proof is going to be the uniqueness. And so, usually to show that something is unique, you pretend there's two of them and show that they must be equal. So, let's do that. So suppose some n can be written as a product of primes in two different ways. So we'll say that n is going to be p1 times p2 all the way to p, let's say, m, and n equals q1 times q2 times all the way to, let's say, ql. So let's say we can multiply some primes together, m of them, to get n, and maybe l different primes. They might be, some of them might be the same, we don't know, to get n as well. Let's say you can do it in two different ways. We want to show that these primes are exactly the same. So, well, both of these prime factorizations equal n, so they must equal each other. Well, let me write that not in red, but in black. So, p1 times p2 times p3 times p4 all the way up to pm must equal q1 times q2 times q3 all the way up to ql. But let me put some brackets here. Remember, multiplication's associative, so I can bracket willy-nilly however I like, as long as it's just a bunch of things multiplied together. So this means that p1 must be a factor of q1 times q2 all the way up to ql. Well, what does that mean? Well, by corollary 39.7, we have a prime that's a factor of a bunch of numbers multiplied together. That tells us that p1 must be a factor of qi for some I from 1 to L. Well, without lots of generality, because we could just rename which prime is which, let's say that p1 is a factor of q1. But since p1 and q1 are both prime, here we are, since p1 and q1 are prime, really it's just because q1 is prime and p1 is non-zero, that means that p1 must equal q1. So we can kind of divide those out if we like. So, just in the interest of time, just continuing like this, we get that Pi equals Qi for all I that's in the set of 1 up to the min of, what did I call it, M and L. And I'm kind of hiding an induction here. So you can show this via induction, but just in the interests of time and energy, I'm kind of hiding that induction. I just want to kind of give you a flavor of what's happening here. But what does that mean? So without lots of generality, let's assume that M is the bigger one, if there is, out of M and L. So what does that mean? Then, well, let's look at this. If M is greater than or equal to L, if M is greater than L, then Pm plus 1, or sorry, Pl plus 1, where is this? Because we canceled out all the numbers, all the primes of index 1 to L, so we just have the ones left from L plus 1 up to M. Maybe I'll put dots there instead. And the only thing left on the other side is 1. But these guys are prime. The P's are prime. And there's no way you can multiply a bunch of primes to get 1. So this is a contradiction. So what does that mean? So that means that M must equal L. Thus, well, we showed that all the primes from P1 up to, say, PL and Q1 up to QL are equal respectively, and M equals L. So thus, we have that each prime is the same thing, so the prime factorizations are the same. And we're done with that. So that's a very important result. Notice there's kind of two parts again. There's the existence of a prime factorization and the uniqueness of the prime factorization. So what we'll do next is we'll show, and I'll just write it up very quickly, how to use these prime factorizations to find greatest common divisors and least common multiples. Alright, so to find the greatest common divisor and least common multiple of two numbers, well, we write the numbers in somewhat of their prime factorizations. What I mean by that is, well, maybe some of these primes, notice I have the same number of primes in each of the prime factorizations, which means, well, how can that be the case? There can be numbers that have different primes. Well, I use the exponents to take care of that. What I mean is that, well, if, let's say, prime pk appears in A, but not in B, then I'm going to include pk in both of them, but I'm just going to set the exponent for pk in B to be 0. So dk would be 0, which means I have no pk's in B, although I have them in A. So there's our setup. We're thinking of p's as our primes and the e's and d's as our exponents. How many of those primes we have multiplied together, even if it's 0 for some of them. Oh, I already have blue, so let's go black then. The greatest common divisor of A and B is, well, it's just each prime to the minimum of E1, D1, and we do that for all the primes. So P1, P2, all the way to PK. Oh, flipped to the min of EK, DK. I'll do an example after this, and the LCM of those, rather than taking the min, is going to be the max. So it's P1 to the max of the exponents times P2 to the max of the exponents all the way to PK to the max of the exponents. All right. So let's just do a quick example to see how this works. So let's let A be, say, 360, and let's let B be 144. Let's find the greatest common divisor of A and B and the least common multiple of A and B. So we need the prime factorizations of both numbers. So let's just do it kind of old school. We'll do a tree diagram for both of these guys. So I guess this is example. We haven't done an example in a while. I think it's 39 point something. I'll call it 39 point question mark because I'm not sure. Okay, so our solution is to come up with a factorization for 360. So 360 I can write as 36 times 10. Well, 10 I know is 5 times 2. Both of those guys are primes, so we'll circle them. 36 I can write as, say, 9 times 4. 9 is 3 times 3. 4 is 2 times 2. Each of those is prime. And remember, the fundamental theorem of arithmetic stated that there's one prime factorization, so no matter which way you do your tree diagram, you're going to get the same factors. So we have 2 times 2 times 2, so that's 2 cubed, times 3 times 3, so 3 squared, times 1, 5, times 5. So that is the prime factorization of 360. Let's do it for 144. And I'm going to cheat a little bit. So I know that the prime factorization for 12, so 12 squared is 144. The prime factorization of 12 is, well, it's 3 times 4. 3 is prime, but 4 is 2 times 2. So I can circle these guys. And then the prime factorization of 12 squared, or 144, is going to be 2 squared times 3 all squared. So that's 2 to the 4 times 3 squared. So I have the prime factorizations of 144 and 360. So the greatest common divisor, remember, we need to find the divisor in both numbers, and it needs to be the biggest. So we need to take the minimum of each prime. And in fact, to go along with our theorem, we see we have a 2 and a 3 and a 5 in 360, but only a 2 and a 3 in 144 as prime factors. So if you like, you don't have to write this, but I'm going to write this just to kind of make it obvious. I'm going to think of this as times 5 to the 0, times 1. I can do that. But now I have the same primes in the prime factorization with some exponents, even if that exponent is 0. So I need the min of each of these primes, so it's going to be 2 to the min of 3 and 4, so the minimum of each exponent of 2, 3, and 4 is, of course, I want blue or black, 3. And then I look at the next one, so the minimum exponent of 3, we have 3 squared and 3 squared, so it's just going to be the minimum of 2 and 2 is, of course, 2. And then I have the minimum of 5 to the 1 and 5 to the 0, so the minimum is, of course, 0. So the greatest common divisor of A and B is 2 cubed times 3 squared, which is 8 times 9, which is, of course, 72. All right. And the least common multiple, rather than taking the min, we're going to take the max of each of those guys. So the max of 3 and 4 is 4, so it's 2 to the 4. Then we have the max of 2 and 2 for the 3s, so the max is 3 squared. And the max of 5 to the 1 and 5 to the 0, which is, of course, 5 to the 1. So this is, well, 2 to the 4 times 3 squared is 144. So 144 times 5. I can think of 144 times 5 as 144 times 10 divided by 2. So that's 1440 divided by 2, which is, of course, 720. You can check that any way you like. I just talked you through the mental math that I used to get there. So the last thing I want to say on this topic is the following note. So, note that if I take the min of, say, or I used E and D, so if I take the min of the exponents, EI and DI, and I add the max of these exponents, well, one of them is going to be the min, the other one is going to be the max, or they're both the same. So it's just the same as EI plus DI. One will be the min, the other will be the max. Unless they're the same, then it's, well, I guess that's still true. But EI then equals DI. So what does that mean? Well, if you think about it, thus, the greatest common divisor of A and B times the least common multiple of A and B is going to be, well, each prime to the EI plus DI, so E1 plus D1 for the first prime, all the way to EK plus DK for the kth prime. Well, I can just separate that out, so that's P1 to the E1 times P2 to the E2, all the way to PK to the EK. So taking out EI copies of PI, putting them together, that gives me A. And I can do the same thing for B. So P1 to the D1, all the way to PK to the DK, which is, of course, A times B. So here's A, and here's B. So that's a kind of a cool fact. And that might help you calculate some least common multiples or greatest common divisors, or whatever. In fact, it's a nice way of calculating least common multiples, so we can say the least common multiple of A and B is just AB divided by the greatest common divisor of A and B. We have lots of ways of calculating the greatest common divisor, so here's the method of calculating the least common multiple. So next lecture, I want to talk a little bit more about primes. We're going to finish up. I want to talk about how many primes there are, which is, of course, infinitely many, but I want to show you how. And I also want to talk about how to determine if a number is prime. So do we have to check absolutely every factor up to that number? And the answer is no, because we have these prime factorizations. That will help us.